Jai Hind, welcome to class of Satellite and Radar Systems. We are studying Unit 2 and this is part 3. Today we'll be talking about satellite link design. So these are the contents of today's discussion. Introduction to satellite link design, basic transmission theory, and system noise temperature and GT ratio, right? So first of all, what do we mean by satellite link? As we know that link in any communication system is the path through which we communicate. Link could be a physical thing, it could be a wireless thing. It is the composition of complete telecommunication equipments that we use, and we have to consider here the parameters that are necessary for communication to undergo, right? So whenever we are talking about any kind of communication system, there has to be a link established between the transmitter and the receiver. Now, what are the factors that affect that link? What are the factors that should be taken into consideration? Like noise is one of the important factor that we consider in designing any of the communication link. So when we talk about satellite communication, there are factors like what weight of satellite is to be launched, what frequency it will be communicating, in what orbit it has to be launched, right? What are the various numbers of antennas that it has, various number of transponders the actual transmitting and receiving unit satellite is composed of, what will be the application of that satellite, and how all that functioning will take place inside it. So a link has to be designed keeping in mind all those things. Along with this, the budget as well, the finances associated. So satellite link design is not a simple process, it's a whole lot of process combined all together to enable our communication satellites to provide the services that we seek for. So as we know that design of a satellite communication system, it's a complex process, requiring compromises between many factors to achieve the best performance. How do we achieve best performance? If we're talking of a system consisting of too much of noise, we must consider signal to noise ratio. When we're launching a satellite into space, weight is one of the most important or critical factor that has to be taken care of. The weight of a satellite is driven by two factors, right? The cost to build and launch a geostationary satellite is about $25,000 per kg. This is what we are talking in respect of geostationary satellite that has to be launched to a specific orbit that we know is approximately 35,786 kilometers of altitude, right? So all these all such data is taken in respect of geostationary satellite. Now weight of a satellite is driven by two important factors. What are these two factors? The number of transponders which are incorporated into the satellite and the weight of the station keeping fuel. So fuel and number of transponder, these are the two most important factors that affects the weight of a satellite. As much as half the total weight of the satellite intended to remain in service for 15 years may be fuel. Just imagine, half of the total weight of the satellite is only because of the fuel, because a satellite has to work around 15 years. A lifetime of a communication satellite is approximately 15 years. In those 15 years, by selling its services, we earn the revenue, right? So there must be sufficient fuel, first to take it into its desired orbit, next for station keeping, right? Three other factors influence system design: the choice of frequency band, the atmospheric propagation effects, and multiple access techniques. These factors are all related with the frequency band, often being determined by what is available. So other three factors are frequency band, atmospheric propagation, and multiple access technique. There's a little difference between multiplexing and multiple access technique. Multiplexing is utilizing the channel resources, it could be time, the frequency, enabling so many messages to pass through a single communication channel at once is what we understand by multiplexing. When we talk in respect of satellite communication, the input channels or the messages are geographically separated. So when we use these input channels or input information from geographically separated regions, we term it as multiple access. So these are almost the same thing, multiplexing and multiple access, right? So the 5 factors we have discussed, the 2 important are number of transponders and fuel, and rest 3 we just discussed, this frequency band propagation effect and multiple access techniques, right? So the information carrying capacity of any radio communication link is determined by the RF power at the receiver input, right? How much information a system carries, this capacity is calculated in terms of power. So whenever we are designing link or we are calculating budget for it, the only mathematical parameter that we rely on is power. This is something very important, that power is the mathematical parameter which is used for showing the relation between input received and output given by the satellite. So power is the foremost important parameter that we use for all our calculation, right? Large antennas are needed to receive weak signals, and the signals from satellite in geostationary orbit are invariably weak. We know that, right? Now early satellites were small and light, carrying small antennas and transponder with low output powers, which resulted in very weak signal. True. So the earth stations are required to communicate for communication within these satellites were large, expensive, and with 25-meter diameter antennas and high power transmitter. What does it mean? We cannot unnecessarily increase the weight of a satellite because cost of launching depends on the weight. So the size of antenna and weight in satellite is limited. But now when we use when we do signal conditioning, signal processing, all has to be done at earth station. Now earth station must be having powerful antennas, right? All the necessary equipments. So that is why we keep some difference between uplink and downlink, and so that up conversion and amplification, so much of amplification and up conversion satellite cannot do. So we do it at ground station. So accordingly we manage the weight. So this is the dimension beyond which we should not go, right? So if we talk about basic transmission theory, the calculation of power received by an earth station from a satellite transmitter is fundamental to the understanding of satellite communications. So in this section we will be discussing about 2 approaches, that is use of flux density and link equation. We can either use flux density equation or the final output equation that will be relating transmitted power and received power, that will be called as link equation. In both the approaches we can study about basic transmission theory. If we consider an isotropic source means it will be radiating uniformly in all directions. If I consider effective isotropically radiated power, EIRP, if I represent it by PT watts, that is P subscript T, this is transmitted power, right? And distance between some receiving antenna and the source, if I represent it with capital R meters, and area of this is area which is receiving it is represented by capital A meter square. Flux density can be expressed by capital F, which is expressed in watts per meter square. So this picture represents flux density produced by an isotropic source. So if we talk about what is link budget in satellite communication system, so one thing this is flux density, one approach, another link equation or link budget equation, one and the same thing. In satellite communication systems there are 2 types of power calculations. Those are transmitting power and received power. I'll take a simple example. If I need particular output I need some amount of output to run a device. I know that value. What should be the value at input? For that, I should be knowing the efficiency of my system. If I need like 50 watt at output to run a device, and I know that efficiency of my system is 50%, at input I'll provide 100 watt. That is, transmitted power must be at least 100 watt, so that at output I do get 50 watt, right? So we must be knowing the efficiency, and accordingly we should give the input or transmitted power, so that received power must be balanced, right? So these are transmitted power and received power. In general, these calculations are called as link budget calculations, and the unit of power is decibel, right? So if we take an isotropic radiator could be an antenna. It radiates equally in all directions, but it doesn't exist practically. This is the ideal situation, that having an isotropic radiator. It is just a theoretical antenna. We can compare the performance of all real antennas with respect to this antenna. So this is a hypothetical reference antenna which we consider whenever we have to do some calculations, right? So there are certain terminologies that we need to understand before we directly jump into link budget equation. First term is power flux density. Assume an isotropic radiator is situated at center of sphere having radius small r. We know that the power flux density is the ratio of power flow and unit area. Power flow per unit area, right? We consider it as sphere, then power per unit area is 4 pi r square, right? Where PS is the power flow, and power flux density of practical antenna varies with direction, but its maximum value will be in a particular direction. These are the we have to consider all these things, right? Another term is antenna gain. What do we mean by gain? Gain could be understood in terms of received power by incident power, right? By taking the ratio of received power and incident power, and both have same value watts, so it could cancel out and it is a unitless entity. So gain of a practical antenna is defined as the ratio of maximum power flux density of practical antenna and the power flux density of the isotropic antenna. This also gain can be calculated, or for any system we calculate gain by taking ratio of transmitted and received power, right? Where here psi m is the maximum power flux density of the practical antenna and is the power flux density of the isotropic radiator, right? Another term that we should know is equivalent isotropic radiated power, that is EIRP. Equivalent isotropic radiated power is the main parameter that is used in measurement of link budget. EIRP is something very important. So mathematically it is expressed by gain multiplied by power, where PS is the power of transmitter and G is the gain of the transmitting antenna. Multiplying gain of the antenna with its power will give me the EIRP value, right? If I want to express it in decibel, that is logarithmic value, this multiplication will change into plus. So this way represented in decibel watt, right? Another term that we should know is transmission losses. What are the various types of losses that we feel in communication, that we face in satellite communication? Most important are contact losses and variable losses, right? The losses which are constant, these are constant losses. There are no other factors that will be affecting it, so we can directly take the values, right? Variable losses depend on the atmospheric things, right? The sky and weather condition is an example of variable losses, right? We have noticed that we all have D2H, right? Direct to home DTH services at our home. We watch TV, and in rainy days we receive zero signal. So because losses increases so much while rain, because rain is one of the factor that attenuates our actual information to maximum extent, so we receive zero. So these are some kind of losses which are variable, that depends on weather. So if we actually go to link budget calculation, what are the things that we should know? If this is an isotropic source where effectively isotropic radiated power, EIRP, is represented in PT, P subscript T watts. Incident flux density is represented as F watts per meter square, because this is power per unit area. Received power is expressed in PR, If I consider this as a receiving antenna, it has area A meter square and gain of the receiving antenna by GR for transmitting antenna GT. These are the this is how we express it, right? So power received by an idle antenna with area this. Incident flux density F is represented by PT by 4R square, and received power is PT by this must be 4 pi R square, right? For area of for sphere it must be 4 pi R square, right? Received power goes to flux into area. This way we can express it. So if we had an idle receiving antenna with an aperture area of A meter square, we would collect power PR watts given by this formula. Power received will be flux multiplied by area, represented in watts. Reduction in efficiency is described by using an effective aperture A subscript E, where A is eta A AR. This term A is the aperture efficiency of the antenna, and the aperture efficiency accounts for all the losses between the incident wavefront and the antenna output port. What does it mean? On the complete surface of antenna, when rays falls, that doesn't get converted into useful energy. We have to consider the effective aperture. If I have antenna of X dimension, the rays falling on complete area will not be effective or will be converted into useful power. So we have to consider the effective area, which will actually contribute to for the power for next stage, right? So from here, if I use the value of A from here, I can rewrite my PR in this term, AE watt, right? So we know that the fundamental relationship in antenna theory is that the gain and area of an antenna are related by this formula, where lambda is the wavelength. Here the wavelength at frequency of operation is given by this, already calculated, right? Now this equation is known as link equation. This is my link equation. This is very important, that my received power is related with my transmitted power with this expression. That is, received power is not directly transmitted power. I'll take a simple example. If my PT is 100 watt and my PR is 40 watt, I know. The question is, how is my transmitted power related with received power? So PT is equals to PR multiplied by some factor, and what is this factor here? Here the factor is 0.4. That is how, if I give 100 watt as input, I'll get 40 watt as output. So PR will this relation between my received power and transmitted power. My received power will not be directly related to transmitted power. My received power will be transmitted power multiplied by some factor. So my received power is transmitted power multiplied by some factor, and what is this factor here? Like here that factor was X, which in this particular case was 0.4. Here it depends on what all things? It depends on GT, that is gain of the transmitting antenna, GR, gain of the receiving antenna, 4 pi R by lambda square, right? It depends on the distance between transmitting and receiving source. It depends on the wavelength, that is the frequency at which we are communicating. So this relation will help me that how much power I should be transmitting so that I get desired received power. So the relation between received power and transmitted power is called as my link equation. This is essential in calculation of power received in any radio link. So this is very important. Now collecting the various factors, we can rewrite this as power received equals to EIRP multiplied by receiving antenna gain by path loss. Now what is path loss? This is expressed in watt. In communication system, the decibel quantities are commonly used to simplify. So multiplication will convert into plus and division will convert into minus, that is power received equals to, in if I represent it in decibel watt, EIRP plus gain of receiving antenna minus LP is path loss. Now path loss will not be a single entity, it will be consisting of so many type of losses, that depends, right? EIRP, what is basically EIRP? When I express it in decibel, 10 log to the base 10 PT into GT. What is gain of the receiving antenna? 10 log to the base 10 4 pi AE by lambda. AE is effective aperture. And what is path loss? 4 pi R by lambda square. 10 log to the base 10, or we can write it as 20 log to the base 10 this. So now more generally I can rewrite my equation as PR equals to EIRP plus GR minus LP minus LA. What are these? These are various losses, right? LA is attenuation in atmosphere, LP is path loss. So actually it's not just the path loss. Along with path loss means the loss that your signal faces while traveling the distance between transmitter and receiver, right? Along with path loss we have different losses like attenuation loss in atmosphere, losses associated with transmitting antenna, losses associated with receiving antenna, right? So this condition is illustrated in next picture. So this is the final expression for link budget, where it has received power is dependent on EIRP, gain of receiving antenna and the losses. Although combiningly we can write these losses, that depends. So this is a satellite link with low noise amplifier, right? If I consider this is my satellite, here EIRP will be transmitting power multiplied by receiving power, and here the loss TA. What is TA? LTA, it is losses associated with transmitting antenna. As I am considering transmitting antenna here, EIRP will be power multiplied by gain. Which power? Transmitted power. Which gain? Gain of transmitting antenna. So EIRP here is PT into GT. Loss for transmitting antenna, losses associated with transmitting antenna. Now when it is traveling, it faces path loss. Different losses are here mentioned, where we face what loss? Path loss in the path. When it comes to atmosphere, earth atmosphere, right? Wind, dust particles, so many things, right? Dispersion, attenuation, scattering, so many things. So these are your atmospheric losses, right? By the time it reaches the receiving antenna will have some gain, which is represented by G subscript R. Now there must be some losses associated with receiving antenna as well. So represented L subscript R, receiving antenna losses associated with receiving antenna. This losses are minus here and this is plus, right? And now to accommodate all these losses we use low noise amplifier. Since now we have been talking about what are the losses associated, and this I have tried to depict with the help of this picture. Now what is the solution for it? If my signal faces some losses, how do I overcome it? We know that we can use filters to chop off the noise. We can use amplifiers to amplify our attenuated signal, right? So LNA is something, low noise amplifiers, that will help me achieve my result. It will help me just amplify the signal but not the noise. So low noise amplifier is something we put at initial or input stage of a receiver. If you remember super heterodyne receiver, a simple receiver diagram in any communication system, after receiving antenna we have a pre-selector and low noise amplifier, then after we have a down converter, right? Receiving antenna, it has a pre-selector, we have low noise amplifier, then we have down converter which we represent with the symbol as well, that is product modulator symbol, right? And after that we have series of band pass filters and amplifiers, and then actual demodulation takes place, right? So low noise amplifier is something we put in the beginning of a receiver module, right? So this is how we calculate link budget equation, right? That's all for today. Thank you.